that we are not covering in this session, but if you want to know about it, we can discuss. Okay, anyway, I prepared this one. I think it's rather easy to look at the hypothesis testing. Okay, so we have explanatory variable or response variable. I think when you have only two variables, when you are looking at two variables, I really don't think which one is explanatory variable and which one is response variable. So let's just make it arbitrary. Okay, just leave it as it is, and we have two variables. So if we have two categorical outcome, two categorical variables, then we can use chi-square or Fisher-Isaac test. Okay. Okay, so when we got two categorical variables, we can either use chi-square or Fisher-Isaac test. Okay, so when we would look at these measures in R software, we'll talk about what are the conditions and how to interpret these chi-square value. And essentially, these are p-values. Okay. Okay, that is when we have two categorical variables. When we have one numerical variable and one categorical variable, and in that categorical variable we have two levels, okay, or two groups. Like we gave an example yesterday, age and sex, okay, male, female. So we got two groups, and we use t-tests, okay. Why do we put t-tests with the plural nouns? Because there are two types, okay, based on the sample. Okay, if you only have one sample, it is a one sample t-test. Okay, that is what we have already looked at the other day, looking at the hypothesis testing for a mean using Z distribution. But here, the concepts are the same, but we use t-distribution. But anyway, there are several t-tests, okay? That's you have to know. So when you are only looking at numerical variable with categorical variable, and if the categorical variable has less than or equal to two groups, then you use t-test. If it is more than two groups, then you use ANOVA, okay? And then the same here, okay? When you have numerical variable and when you have categorical variable, you use the same, okay? Okay, when you have two numerical variable, you use correlation test. Okay, so this is when the conditions are met, you can use this, okay? When the condition for each test are met, then you can use these tests accordingly. But what if the conditions required for the central limit theorem or each test is not met, okay? And then we use alternative non-parametric test, okay? Or alternative test, okay? Okay, here we use the term non-parametric. Previously, this slide, these chi-square tests, t-tests, okay, ANOVA, correlation, these are called parametric tests, okay? Why we call parametric tests? Because when we look at the t-distribution or f distribution or chi-square distribution, these are already known parameter, okay? Let's think about z distribution. Yesterday we find the test statistic z and look at the p-value, okay? Where do we look at the p-value? P-value for the normal distribution, which is standard at 0 and standard deviation is 1, okay? So these are the population parameter, okay? With the mean population mean 0 and standard population standard deviation 1. That is what we are comparing. This is called a theoretical distribution. So we know that, I mean, we theoretically know that parameter of the population. So we compare our z-score based on that parameter. That's why we are calling these tests as a parametric test. But anyway, these are not important, okay? So first, we need to, based on the type of the data you have, we need to think about this test and check their conditions. If the conditions are met, then it is okay. If they are not met, then we can use alternative tests, okay? Alternative tests. Okay, so when we have categorical, two categorical variable, the first test is chi-square or Fisher AZ test. Okay, but when the conditions are not met, you can use maxima test or even the AZ test. Okay. Okay. Again, when we have a numerical variable and a categorical variable, with group is less than or equal to, we can use Wickhausen test. Okay. There are two Wickhausen tests. Like there are two tests for two t-tests, right? T-tests for dependent sample. So if our observation, because we are looking at two means, okay? We are looking at two means. So if our observation are dependent of each other, if the two are dependent, then we use t-test for dependent t-test. If they are not dependent or they are independent, then we use independent t-test. Okay, so there are two tests. The same way, we also have the alternative corresponding tests, Wickhausen test, Wickhausen sign rank test, and rank sum test. Okay, anyway, if we have more than two groups, we call Crusher-Wallace, okay, for ANOVA, which is the alternative for ANOVA. Okay, the same here, numerical and categorical variable. When we got two numerical variable, we use correlation test. Okay, anyway, the previous one is called a Pearson correlation test. Okay, this one is can be either Spearman correlation test or there is another correlation rule test. Okay, so anyway, yeah, this is just to give you an idea. Okay, there are several other hypothesis tests based on these data types, but these are the commonly used type, and we are going to look at how to do each test. And I mean, we will demonstrate how to do these tests in R. Okay. Okay. Anyway, let us go to the File Explorer. Okay. So starting this point, everything where we will discuss in detail in R. Okay. So go to the logit drive C, and then we already created exercise _SWR folder. So go there, and then I think you have SWR day 7. Okay, so you copy. Okay, let's do that again. You copy this, and then you paste and give it a new name. Okay, so this is what day 6 week 2. So say, okay, week 2 day 6. Okay, week 2 day 6. Okay, and do that and double click it. And we will look at in RStudio. Okay, so when you have opened it, what we want to do is we were just going to delete everything, okay, except these setup, okay, up to reading the data set. Remove. Okay, so we will use the same data set. because there is a big data set with 25 variables, okay? So we will just use it. And okay, I think okay, so from this point, what we are going to do is we are going to give a session, okay? So Control Shift R. And then we will say that it is the say it is a bivariate analysis, okay? But we will call it as an inferential statistics, okay? Okay, this is bivariate analysis, inferential statistics. Okay, so anyway, please note here that we haven't managed our data, okay? We just go straight to the inferential statistics. That is just to give you an idea how to do it in R and interpret it, okay? Okay, so why don't we go with the first one? Okay, so the first one is okay, here I think I'm going to talk a little bit about how we are going to do this, okay? So first, we try to do this using base R, okay? Then second, for some tests, okay, some tests, we will do it in Amsterdam, using Amsterdam, okay? Okay, so anyway, for any test, we will do it 2 times. First, we will do it using base R, and second, we will do it Amsterdam. But basically, this should give you the same, okay? This should give you the same. Okay, so anyway, first let us run everything here. Run. And where should we start? Let us start with the t-test, okay? With t-test. Okay, so I already said that when you have one to use, okay? When to use t-test. When you have one continuous variable and one categorical variable. Anyway, we are looking at 2 variables for this one. And to use t-test, category should be only 2 categories, okay? 2 categories or less. If it is more than 2 categories, we use ANOVA. Okay, that is the rule. Okay, now what are the conditions? So t-test is basically these are parametric tests. So parametric tests all based on the central limit theorem. Okay, the one we will be talking about here, all parametric tests based on the theoretical distribution, which is central limit theorem. Okay, so we follow central limit theorem assumption. Okay, so what are the central limit theorem assumptions? First one is independence. Okay, and the second one is sample size. That we already know. Okay. Okay, so in this case, for t-test, we also need to look at the one more condition, which is called the homogeneity of variance. Okay, so consider about this. You have 2 groups. Okay, consider our example, age with sex. Okay, so anyway, we are going to demonstrate with age and sex. Age versus sex. Okay, sex, we have male and female. So consider about this. When you have male and female, there are two groups, okay? Two groups. And for each group, there are different means and different standard deviation, okay? Okay, standard deviation is another measure for the variance, okay? Variance is another measure for the spread, which we haven't taught in descriptive statistics, but standard deviation is similar to variance, okay? So consider there are two groups, and when we want to compare two means, okay? So the conditions of the standard deviation or variance in each group is important, okay? Why important? If the variance are not equal, then we need to adjust for that one, okay? Okay, so that is the condition for the homogeneity of variance, okay? So here the assumption should be the variance should be equal, okay? Assumption here is variance between two groups should be are equal, okay? Okay, so these are the general t-tests, okay? The condition for the general t-test. Okay, if these conditions are met, what will we use, okay? If these conditions are met, we use independent t-test with assumption variances is equal, okay? Okay, second, if not met, we use pair t-test, okay? Or we call it independent t-test. Okay, sometimes they also use the two sample, okay, because we have two groups. So these are sometimes called as independent two sample t-test. Okay, these are also the same. Pair two sample t-test. Okay, so anyway, let's do this for our age and sex, okay? So first, we need to consider the independent assumption for our data. Okay, independent assumption. So do you think in our patients data set, do you think male and female are independent of each other? Well, actually we didn't have any context for this data, right? But we assume that they are not related, okay? First, for the purpose of demonstration, okay, we will assume. Yes, Sashi?
In line 35, here t-test is independent or dependent t-test. Here.
Oh, sorry, yes. Thank you. So this will be a pair dependent t-test, okay? Not independent t-test. Okay, so basically we have to check the condition, okay? First, we check the independence assumption, okay? Right now we assume that it is the independence assumption, okay? That the two samples are not dependent of each other. Okay, so second, sample size. We have 130, okay? 120 sample size. So which is sufficiently large. Okay, and then we also need to check. Okay? We also need to check the normality test. The normality test, right? Because for the independent assumption and for the sample size assumption, we also need the normality, whether the distribution is normal, the distribution is normal or not. And based on this, we determine if our sample size is sufficient or not. Okay. Okay. So now, for the assumption 2, we also check normality. How to check normality? First, you can do the histogram. Okay. Okay, so we will check patient. Okay, so we will use the piping function here, and then we use width because we are going to look at a histogram. Okay, so and we will run this. Okay, so here we have the invalid value, right? Okay, so let's try and fix this up here. Okay, so here what we will do is we will also fix our data at the same time. Okay, data management, and then we will say that patient. I think we already discussed this several times, so I will just write. Okay, patient. If you don't understand it, then refer to the videos on week 1. Okay, we extensively talked about how to use piping function and how to replace the value. Okay, but I think the comments are pretty intuitive here. So we will replace age with an A if age greater than 100. Okay, basically that's the idea. So okay, anyway, we need to run this. Okay, so run everything. So let's run again. So looking at this distribution, I think we were assigned to the same object. Okay, we were assigned to patient data set. We won't give it a new name. Okay, because otherwise it will be a little bit confusing. But to counter the so to do this, we need to run from the top to bottom every time. Okay, so that's why I run all the code every time we assign this. Okay, for this we didn't assign it, so it's okay however we run it. Okay, we didn't assign it. So for any assignment code, we will run top to bottom. Okay, so based on this data set, is fairly normal, right? Okay, so this is fairly normal. Okay, so I think our normality assumption is met, but again, it is by histogram. Okay, it is by checking with histogram. And second way, how we can check by using hypothesis test. It's called the Shapiro-Wilk test. Okay, Shapiro-Wilk normality test. Okay, anyway, how do we do this? We can use MSTAT. Okay, so for MSTAT, you just summarize it. Summarize age. Okay. Okay, so let's look at here. I think let's run this again. Okay, so on week 1, we didn't discuss about the normality test. Okay, so the sum function from MSTAT also provide the normality p-value. Okay, normality p-value. So say we have 0.155. Okay, that is overall. Okay, overall. So what does it mean here? Okay, what are we testing? What are we testing is we want to, so that null hypothesis is that the data is normal. Okay, the alternative hypothesis is the data is not normal. So the p-value here indicated 0.155, which is greater than 0.05. Okay, so we cannot reject the null hypothesis, which is normal. So we say that this data is approximately normal. Okay, and this is this is the overall, and then we also should look at the group summary measure. Okay, group normality. So okay, we will write patient and age. We will look at based on sex. Okay, but again, we also have the 12.2 invalid value here. So what we will change here again with sex and with NA if sex is equal to 12.2. Okay, and then we will run everything. Okay, so now we still have this NA, so we'll just remove it, but anyway, it's okay, right? Okay, so you see for each group, we have a normality test, and this is normal, okay? So every p-value is above 0.05. So we can say that it is normal. Another test, okay, there a few, another way to visualize it using the QQ plot, okay? Quantile plot. So the same, you can do the same QQ plot. So what we do is we will use with command, and you have to put the data set patient, because in QQ plot there is no data set argument. So QQ plot and then age. Wait a minute. Okay, I think we need to run something like this. Why is it run? Okay, let me try this. I think it should run. Okay. So no. Okay, this is not correct. What we have to do is QQ norm. Okay, so first, why don't we try this QQ norm? We cannot directly do QQ plot. Okay, so we do this. Okay, not a QQ plot. Okay, so QQ plot is when you have two, you need to give it two value, okay, at least two inputs. Okay, the first input is your quantile, original quantiles, and then second one is the theoretical quantile. So we cannot use QQ. This is the QQ plot, but the common is QQ norm. Okay, and anyway, when we discuss QQ plot, we still need the diagonal line, right? So to add the diagonal line, diagonal line. Okay, to add the diagonal line, you do this. Okay, I think this one like this. Okay, uh, 0 and 1. Okay, so we give it the apply, okay, with a function apply, and then we run this 0 and 1. Okay, okay, I think it should come. Okay, to add a diagonal line, what you can do is QQ line. We give it patient, and then we give it QQ line age. Okay, so okay, at least this what we can. Anyway, okay, we will delete this. We'll delete this. So this is how you do how you check the normality. Okay, otherwise everything is quite normal. So we check the independent assumption, we assume that it is independent, and we check the sample size is large, and we check the normality with three methods: by histogram, by using Shapiro-Wilk test. Okay, and then anyway, you don't have to do everything. Okay, you just look at the histogram, and if it is nearly normal, you can just go ahead. Okay, there are three ways to check the normality, and then the third assumption, is the homogeneity of variance. Okay, that is basically variances are equal in two groups. Okay, so how to test this? There is a test called the variant var dot test. Okay, in R. So we will look at it. Okay, var dot text, and then we will use this one. Okay, so we will have to put the formula and then data. Okay, so because there is a data argument, okay, so we don't need to use with. So var dot test, and then what is the formula? We want age, okay, categorized by sex, okay, and then data is patient. Okay, so let's run this. So you can see that the variant test, which is which use the F test, okay, which use the F distribution. So that is the output for F test, which we are not going to discuss in detail. Okay? We're not going to discuss every detail here. But what we are going to do is look at the alternative hypothesis. Okay, so the alternative hypothesis, true ratio of variances is not equal to 1. Okay, so how do we test the variances between two groups? We divided each other. Okay, we divide two variances of two groups. And then our null hypothesis is this ratio is equal to 1. Okay, alternative hypothesis is this ratio is not equal to 1. And then we have our p-value, okay, here. Okay, our p-value suggests that there is no difference between, there is no the variances between the two groups are not different. Okay, so we got the p-value. Okay, we are going to copy this. So let's say that, okay, p-value is equal to 0.025. So we know that it is variances between, you can just say the variances assumptions matter. Okay, variances between male and female are the same. Okay, so now, okay, I didn't notice the time limit, so it automatically stopped. Anyway, what we are doing is finally we can test our data using independent t-test with with same variances. Okay. Okay. So let's look at the t-test. Okay. So what is the function for t-test? This is coming from the base R, not from Amstat package. Okay. Okay. Let's look at student t-test. Okay. So we can use this, okay, because there is a data formula. So we do not have to use with function, okay. So we say t-test, and we need to put the formula, okay, like here. So we say t-test h, and then the tilde sign, okay. This one is called the tilde sign. It is above the tab key or below the escape key on your keyboard, okay. So age categorized by sex or group by sex, and then we use our data patient. Okay, so this is how you use the t-test, but we need to specify a little bit. Okay, that we say. Okay, let's try. Let's see what this give us. Okay. So ignore these messages, okay? Because there is a block open, then and we ignore it. So just ignore this one message. Okay, we say that whilst do sample t-test, okay? It is whilst do sample t-test, and then t value, okay, instead of z value. It is the same as our our test statistics z that we saw yesterday. And then based on this, we look at the p-value, okay? And then the null hypothesis would be the average age for a male and average age for female are the same, okay? And then alternative hypothesis is here it is written that true differences in mean is not equal to 0, okay? Okay, so we have mean in group female and mean in group male, okay? So we have a difference. And then when our null hypothesis is this is equal, okay? Our alternative hypothesis is it is not equal. And then we have a p-value of 0.414, which is not significant, okay? Which is not significant. So it means that the average mean between the two groups there is no difference, okay, statistical difference between the two mean. Okay, so this is the result that is given by R. So you just look at the p-value, and then if p-value is less than 0.05, okay, because we are looking at 95% confidence interval, and then you can change these 95% confidence interval. So if it is less than 0.05, then we say that the two groups have different means, okay? But here we have value greater than 0.05, so we say that two groups are the same, okay? But we also need to account for the same variance, okay? By default, it is given with the same variance, okay? Variance assumption is equal to true, okay? So let's look at let's look at in another one, okay? Test age, sex, and then data is equal to patient, and then we will say that if you go here, you can say that var equal to false, okay? So we need to put that var dot equal is equal to true to make our assumption variances for variances, okay? We say that here in for that condition, we say that the variances are equal between the two groups, okay? So we have to specify that variant var dot equal is equal to true, okay? So look here that how this will change, okay? So the first function, we didn't specify the variances, equal variances assumption. So we t-test gave us 1:2 sample t-test, okay, which is already accounted for homogeneity of the variances, different variances, okay. But we do not want to account for that variances, different variances. So we specify it to variance does value equal to true. So you can see that p-value is a little bit different, okay. P-value is a little bit different, but in some cases, when your p-value is on borderline, okay, 0.05, and say when you do not consider the p-value, it is greater than 0.05. When you consider variance is equal, then p-value is less than 0.05, okay. It gives you the opposite p-value. So in that case, you need to look at all the assumptions, and based on the assumption, you need to decide whether assuming very equal variances is correct or not correct, okay? And then you choose the correct p-value, okay? So this is how you consider the variances equal assumption, okay? With this one, so the value is slightly different because in a formula we account for the variances, equal variances assumption. Otherwise, I think there is not really change much, okay? The same interpretation. Okay, so this is the independent t-test, okay? What about the dependent t-test, okay? What about a dependent t-test? Dependent t-test. Okay, here we will change to the argument, okay? We will say that it is pair data or not, okay? Pair or not. So the same command t-test is group by sex, and then data is patient. And we have to say that, okay, this is assuming that male and female are dependent on each other, okay? Say that this patient data, we call it the couple data, okay? We call it the married couple. So male and female are married to each other, okay? Let's consider that, okay? Let's assume that. And then we can say that, here you can look at, we can say that pair is equal to false when we have to set it to pair is equal to true, okay? And then run this, okay? But anyway, you can see that there is a complete dot case, there is an error saying that complete dot case X and Y, not all arguments affect the same length. Because in sex, we have a missing value, right? We have the missing value. So actually, we need to remove this missing value, okay, before we do this. So one way to do this is, because this one give us an error, so we will comment it out. One way to do this is to filter it, okay, filter. We do not want H is missing value, okay? Okay, so how to do this? And we will filter if H is not equal to missing value, okay? We filter if H is not equal to missing value. Missing value is any, okay? So how do we write this? Do we write like this? Okay, this is wrong. Okay, so we will say that this is wrong. Okay, we do not write to check like this to check the missing value. Okay, to check the missing value, we say is dot NA. Okay, age. There is a function called is dot NA. Okay, this will give you all missing value. But when we do not want missing value, so we put not symbol. Okay, so we filter age not equal to missing value. So not equal to, we say it is missing value and then age. Okay, so this will remove the age, and now we can use the t dot test, and then the same line. Okay, but the data should be dot because we use the piping function. Okay, so the data now should become dot, and pair should be true because this is the pair t-test. Okay, wait a minute. Complete dot case is an no argument have the same name. I think this is essentially because we have the paired argument true. We need to have the same length on both sides, right? This is how to give you an example. Okay. So anyway, this is not working. So we need to change the example. Why don't we change this to married? Okay, I think we do not have any. Oh, okay, I got it because the age, there is also mixing value in sex, right? Okay, I think we also need to remove the missing value of, okay? In age, also in sex, we have both missing value. So we need to remove all missing value, okay? All observation with missing value. So that is what that complicates me, okay? Anyway, I think this, okay. So it's not happening. Okay. So missing value is a little bit tricky to look at. It's 180 observation filter. I wonder if we have other, let's look at it. Do we have other variable that we can use? Okay, what about BMI? Okay, I think age is not working because of the missing value. And still because I do not want to take times, so we'll just change it, okay? Because there are other arguments that you can pass, so you can just remove the missing value here, but I will just check and then I will tell you tomorrow, okay, how to do this. And I need to check it. Okay, so let's try with BMI and merit, okay? Because these are not, there is no missing value in these variables. So BMI and then merit, I hope this works. So data should be our patient data and it should be true, okay? Oops. Okay. Here we have the NA.action, right? Okay, so NA.action, I think, okay, we got it. So what we have to do is na dot Ashin is equal to, we have to say na dot omit. Okay, we have to remove the na value. Huh. Still it's not working. Hmm. Check. Hmm. I wonder why it's giving us error. And get options. I need an option. A function which indicates okay, I think this one should be like this, okay, without quotation. Hmm. Pair. Okay, sorry for that. Logical, this is true. Cognitive. Hmm. Any idea? Any idea why this it is not working? You sure? It is? No. You mean this? And still there's an error. Okay. When we remove this one, the parity test, independent test is working well, right? So yes. Okay, put it in a bracket. Uh,
It is
that is no. Okay, I think that is. Yeah, still not working. Okay. Now I think we still need it because we are using this. Okay. Anyway. Okay. Anyway, there is no working, so let's remove this and we'll try another way. Okay. We'll try with t and then use the age and then sex. Okay. And then pair is equal to true. Okay. Oh, I see. I see. X and Y is not numeric. Okay. Obviously, it's not working. Yeah, but this is wrong, okay? Because you are already subsetting and then you also give the data, okay? So, so you see, you are using patient data and you are already subsetting it, okay? So this is wrong.
We can remove that data argument, I think.
Yeah, you can remove the data argument.
Data argument and run it.
That is also another way. Okay. Okay. So I think there is a bug in this formula. Okay. So currently when you specify data, we are using this one. Okay. So we cannot use both, but it still run because the data argument is not counted here. Okay. So when we run this, we are essentially using this one. Okay. We are essentially using this one. Okay, anyway, so this works, so I think it will be fine. Okay, so and then we also have to say that variance is equal to true. Okay, let's see, var dot equal is equal to true. Okay, anyway, there is no difference. Okay, whether you put the variance assumption true for the pair t-test. Okay, so the value are the same, p-value are the same, t statistics is also the same. So you can see that. Okay, why don't we compare this with the I think we can check with age, right? I think it should be okay now. So this should be the final one. Okay. Okay. So okay, I don't know why it didn't work, but maybe because we didn't read the documentation. But apparently it should work. So there are two methods that they implement t-test. Okay, the first one is what we have written here. Okay, you gave x and y value, but apparently it didn't work with the width function. Okay, it should work with width function. Okay, anyway, the second one is using the formula and then put a data set. Okay, I think there is some error in the code that they have written, so it is not working. So why don't we compare this with the pair true and not true? Okay, true and false. Okay, so the first one we run with true, the second one we run with false. Okay, so as you can see that these two how do we say these two tests slightly give a different test value. Okay, p-value is not different because this is just a coincidence, but t and t-test is different. Okay, 88 to 89, and then degree of freedom is also different. Okay, this is because they adjusted for a pair t-test. And then when you look at this one, they say that mean of the differences is 50 point this one. Okay. Okay, so this is how you do t-test, pair t-test or independent t-test, and it depends on the condition that you are setting. Okay. Okay. So next, I think we will quickly go through the nonparametric test for these nonparametric tests for these two t-tests. Okay. Okay. The first one is they are called a workout syntax. Okay. Workout syntax. So this is the workout rank syntax and side rank test. Okay. Okay, so the same here. Okay, we will just use the same parameter and then we will change this to Wilcox-Dawes test. Okay, and then this is for the independent sample. Okay, for a dependent sample, the same. Okay, so this is for demonstration. When you do the analysis, you don't have to do everything. Okay, you just have to look at the assumption, and if the assumptions are not met, then you have to continue with the nonparametric test. Okay, so you can see that when the condition for the parametric test is are satisfied, then the values are not that different. Okay, p-value gave you the same p-value. So essentially it is saying that there are two groups, married and not married. Okay, two groups. So the mean age between married and not married group are quite different. Okay, so p-value is quite significant. So there is a real difference in a population. Okay, this is how you do this. Okay, so anyway, you have to look at the documentation. Okay, if you're not used to doing this, I think even so you will find errors like we did. Okay, anyway, all these can we can do this in AMSTAC using the sum function. Okay, so we can say that sum patient age, and then we group by sex. That's it. Okay, but here we didn't remove any value, so it assumed that there are three groups, so it gives you the ANOVA and Crystal-Wallace test. Okay, so we need to tell that, okay, we need to remove that missing value. Okay, how to remove that missing value? We say filter, then we say not equal to, and then we check if sex is equal to missing value. Okay, and then we take the opposite of the missing value, and then we say, okay, we were trying to sum it. Okay, so we can write this way and then run this. Okay, so anyway, it will give you the same. Okay, anyway, this is for sex, right? Sorry, now we are trying for married. So I think this will give you the same p-value. Okay, and it doesn't give you the same p-value. Or does it give you the same p-value? Wait a minute. Okay, I think we have confused a lot of things. Okay, this was age and sex. This is age and sex, and then we say this is age and sex. This is approximately 2 sample t-test. Okay. Okay, I see. Okay, so I think, okay, I got it. So the function sum from Amstrad give the t-test with the different variances. Okay, that's why was two subit. So it did was two subit tests, not the. It didn't account for any variances. Okay. Okay. Anyway. Okay. Anyway, I think that is how you do the T and Wilcoxon tax in by Amstrad. Because Amstrad you didn't have a lot of flexibility, like you cannot change the assumption like the Petty test or even the variances assumption, var or equal, it just gave you the default, the Welch test, okay? And then for merit, I'm not sure why it gives us the p-value less than 0.05. Okay. Anyway, these two p-value does not match. Okay. Anyway, Anyway, let's call it a day, and tomorrow we are going to look at let's look at the t-test and Wickhausen nonparametric test again. Okay, I think today because of the error, I think a little bit confusing, so let's try tomorrow again. Okay, so I think this is it, and let's see tomorrow. Okay.